Most walkers skip right over them. River-worn, grime-covered pebbles that look like nothing more than the detritus of erosion. But in mining runoff zones, slag heaps, or even roadside ditches near old kimberlite fields, a dull, waxy exterior might not just be a weathered rock. It might be nature's accidental camouflage for a high-value core. The missed opportunity lies in the assumption that if the surface is unremarkable, the stone has no worth. In reality, some of the highest purity rough diamonds have exited the earth shrouded in thermally reactive coats that hide every diagnostic trait from the naked eye. The reason this happens traces back to the violence of geological transport. As diamonds travel upward through volcanic pipes, particularly kimberlite or lamproite, they are often caught in a chemical storm. Silica-rich vapors, iron oxides, and hydrothermal fluids begin to settle on their surfaces. If that journey continues through erosion and sedimentation, the outer layer thickens, hardens, and mineralizes into a kind of secondary skin. In mining slag or tailings piles, especially those processed under older techniques, residual diamonds may remain coated in vitrified silicates or industrial residues that mimic worthless rock. To the untrained eye, there is little to distinguish these from junk, but even slight anomalies can offer a hint. For example, a stone that feels heavier in hand than its volume suggests, despite a dull surface, deserves closer scrutiny. Weight-in-hand intuition, developed through repeated handling of quartz, 2.65 Sg, feldspar, and other common matrix materials, becomes a crucial first filter. A stone that feels too dense for its size may house something with a specific gravity above 3.4, possibly even near 3.52, the Sg of diamond. Other field cues include subtle symmetry in shape. Nature rarely forms perfectly smooth ovoids in hard matrix unless they've been mechanically tumbled. So when a rock seems too evenly rounded or reveals straight-edge geometries beneath grime, it may point to artificial handling, or an angular core resisting erosion within a malleable outer shell. A gentle scrape with a knife may reveal a glint, but this is often misleading. Surface oxidation on glassy coatings can also produce a misleading sheen. Only deeper methods, specifically thermal exposure, will force the outer shell to betray the core beneath. That thermal vulnerability is precisely what separates coated diamonds from naturally hard surface stones. Unlike quartz or corundum, which are thermally stable even at torch temperatures, feldspathic glass coatings, volcanic tough residues, and industrial slags can blister, craze, or soften under direct heat. The moment of transformation, when an inert lump begins to fracture, melt away, or even flake under controlled flame, signals the possibility of a core worth preserving, testing, and ultimately verifying. Some stones resist every signal. They don't glint, they don't crack, and they don't offer weight clues. But even these can hide high-value cores if you know what surface details to watch for. The tell isn't always flashy. In fact, one of the strongest indicators that a coated diamond lies beneath is subtle. A misleading surface luster that seems off or wrong for the environment it's in. Many people overlook these discrepancies because they expect brilliance, forgetting that diamonds freshly extracted from volcanic pipes or slag environments rarely look anything like the cut stones in a jeweler's case. Instead, what often betrays them is a kind of unnatural geometry, especially in stones collected from contexts that favor chaotic wear. In a typical riverbed, most stones exhibit irregular, weather-worn outlines. But coated diamonds, shielded by resilient yet heat-reactive outer layers, often retain fragments of octahedral symmetry. Look for faintly flattened faces, point-like terminations under grime, or edges that seem too straight to be accidental. These are remnants of diamond habit resisting mechanical weathering while the coating absorbs the abuse. Under strong light, ideally direct sunlight or a flashlight with narrow beam spread, rotate the stone and look for inconsistencies in luster. A feldspathic or glassy coating may show dull waxiness overall, But even a partial flake or thin zone might reveal a flash of adamantine reflection, that near-metallic gleam unique to diamonds. Importantly, this is not the oily or greasy shine seen in serpentine or opalized matrix, which often tricks beginners. Diamond's luster is hard-edged and bright, never smudged or wet-looking. A field loop can sometimes reveal the boundary between outer rind and internal core, especially if the coating is a different mineral class, such as iron oxide over carbon. In such cases, tiny fissures or spider webbing in the surface can signal internal pressure differences between layers. This is most common in stones retrieved from iron-rich volcanic flows, where diamonds may have accreted hematite or limonite shells during high-temperature deposition. When you see pitting in a near-uniform rind, or fractures that seem too localized, it suggests an internal structure that resisted the expansion or cooling forces which shaped the rest. A simple field test to reinforce suspicion is the wet/dry visual contrast. Soak the specimen in water, then observe it as it dries. True coatings that are different from their cores will often exhibit differential drying rates. Porous or oxidized rinds will darken and stay moist longer, while denser diamond interiors may cause water to bead and evaporate quickly along exposure lines or flaked zones. Still, not every odd stone is worth testing. The goal is to identify the confluence of signals: unnatural symmetry, inconsistent luster, density disparity, and surface crack patterning. When these align, the next step is controlled thermal exposure, not just to destroy the coating, but to read its reaction. The transformation begins in environments most people dismiss: the interiors of volcanic pipes, the cooling edges of lava flows, or the slag byproducts of early mining operations. In these zones, diamonds don't emerge pristine. Instead, they often exit the earth sheathed in coatings that form through complex geological or anthropogenic processes, each with its own thermal behavior. Understanding these coatings is essential not just to identifying concealed diamonds, but to removing the outer layer safely and effectively without damaging the stone beneath. One of the most common and misunderstood coatings is vitrified silicate, a glass-like skin that forms when high silica volcanic ejecta cools rapidly around a harder core. In kimberlitic eruptions, diamonds near the vent can become embedded in a molten flow of feldspar, quartz, and other silicates. As this mixture cools, it contracts around the diamond, creating a brittle shell that mimics dull quartz or pumice. These coatings can be nearly indistinguishable from the host rock unless heated. Under flame, vitrified silicates may begin to craze, developing fine surface cracks, before flaking away entirely as thermal expansion mismatches stress the bond. Another key type is iron oxide crusting, often reddish or brown, and formed through the weathering of ferrous materials in the stone's surroundings. In mining slag or tailings, where iron and carbon coexisted at high heat, residual diamonds may take on hematite or magnetite-rich coatings. These are often magnetic, weakly so, but can show vivid reactions under heat. As temperature rises, they may spall in flakes or darken visibly before detaching. However, the risk here is that uneven heating can cause pressure fractures in the diamond itself, especially if the coating contracts asymmetrically. A third variety is clay silicate composite, frequently encountered in subduction zones or river-transported stones. These coatings are softer but denser and tend to conform tightly to the core shape. They may contain trace serpentine, talc, or mica, making them appear waxy or greasy when wet. These crusts don't melt so much as dehydrate and crack when heated. Look for steam pitting or sudden dulling as indicators that thermal breakdown has begun. If the core is indeed a diamond, it will remain unscathed, thermally stable well beyond the temperatures needed to disrupt the matrix. Industrial slag coatings present another unique case. In regions with legacy mining or smelting operations, discarded material often includes diamonds accidentally captured in waste flows. These stones can be encased in synthetic vitreous compounds, sometimes with high lead or barium content. Under flame, they may emit colored vapors or leave residues. Safety is critical here. Use proper ventilation and avoid inhalation. But if handled cautiously, such coatings may melt away completely, revealing gem-grade cores beneath a shell no different in appearance than shattered glass. The formation of these coatings is neither random nor rare. They are the result of specific pressure, temperature, and chemical conditions, and they are more common than most prospectors realize. Their presence acts as both a mask and a clue. If you recognize the coating, you can predict the best way to remove it and assess the probability of a diamond within. Striking a stone with heat is not about blasting it. It's about coaxing the outer layer to betray what's within. Rushing the process risks thermal shock, and while diamonds themselves can withstand intense heat, up to 1,300 degrees Celsius in controlled settings, the coatings surrounding them often can't. That's the goal. Exploit that weakness without pushing the diamond to fracture from internal pressure differentials. A field-ready heating setup doesn't need to be elaborate, but it must be deliberate. The simplest and safest method begins with a butane micro-torch, compact, consistent, and widely available. Unlike propane torches, which burn hotter and less precisely, butane provides controllable heat ideal for testing unknown specimens. Always mount your sample on a non-flammable base, ceramic tile, fire brick, or a folded steel mesh tray. Elevate it if possible to allow airflow beneath, reducing the chance of heat pooling under the stone and causing base scorching or flashback. Position the flame tip roughly 2 to 3 centimeters from the surface and begin with a low-intensity, sweeping motion. Direct contact with a narrow flame point can cause coatings to expand too fast, spalling fragments that may damage the diamond if trapped between layers. Instead, aim to heat gradually across the whole surface, allowing thermal gradients to build naturally. A visual cue to watch for: the coating may darken, begin to blister, or crack audibly. This is your cue to slow down, not speed up. At this stage, the outer matrix is entering failure mode. For thicker or more vitrified coatings, increasing intensity in short bursts can help. Always pulling back the torch for a cooling interval every 30 to 60 seconds. Use a metal pick or tweezers to gently tap the surface between cycles. If flakes detach or a glassy coating begins to shatter, you may glimpse a reflective or geometric core. Avoid prying. Let thermal cycling do the work. For safety, always wear impact-rated eye protection. Some coatings explode off in sharp shards, especially if silicate gas pockets were trapped during original formation. For more fragile field environments where open flame isn't practical, such as forested terrain or windy ridgelines, use a solar lens, 6 to 10 centimeters magnifying glass, to concentrate sunlight on a point no larger than a dime. While this won't melt glassy coatings, it can dehydrate and crack clay-based rinds or alter iron oxides enough to expose color and texture shifts. This method is slower but safer and allows high-contrast observation without soot or smoke. In lab-adjacent conditions, a small electric hot plate with a temperature-controlled setting provides a non-flame alternative. Wrap the stone loosely in aluminum foil to concentrate heat and place it in contact with the plate for 10 to 15-minute cycles at 400 to 600 degrees Fahrenheit, is almost equal to 200-300 degrees C. Observe for signs of surface oiling, bubbling, or color change before escalating further. Thermal paste applied to the base can stabilize heat transfer and help prevent rolling, which is crucial if the stone begins to crack unexpectedly. Throughout any heating method, track time and temperature mentally or with tools. If after 10 minutes of stable heating no visible change occurs, no blistering, no color shift, no flaking, the coating may be inert or the core may not be diamond. But if the outer layer gives way and reveals an angular form, a flash of luster, or an unusually clear fracture plane, the next step is confirmation. The moment the outer layer begins to yield, every second matters. A faint crack, a sudden blister, a shift in surface gloss. These are not cosmetic changes, they are diagnostic. Thermal exposure is not just about removal, but about observation. The way a coating breaks down tells you as much as the core it hides. Recognizing the right visual and tactile cues during heating separates an accidental burn from a controlled revelation. First, pay attention to color transitions. Coatings composed of iron oxides often shift from deep brown or red to a dull black when heated beyond 250 degrees Celsius. This change is more than cosmetic. It marks the phase transition of hematite, Fe2O3, into magnetite, Fe3O4. If that shift is accompanied by visible cracking or separation, it suggests a layered structure, typically coating over something denser and more thermally inert. When that core resists color change and continues to reflect heat, you're likely observing a diamond or other refractory material underneath. Next, note the blister pattern. Feldspathic or silicate-rich coatings will often begin to bubble before they fracture, especially if trace volatiles were trapped during their original formation. These blisters are small, translucent domes that may rupture silently or burst with tiny puffs. If blistering occurs asymmetrically, favoring one side of the specimen, it may indicate internal heat redirection from a dense core deflecting the gradient. That's a strong signal the heat is reaching a boundary layer between coating and valuable mineral. Once the core is exposed, immediately begin second-tier diagnostics. Start with the conductivity probe, thermal and electrical. If the thermal conductivity test reads positive and electrical reads negative, that's strong evidence for diamond. If both light up, moissanite is likely. No signal on either? You're probably dealing with zircon, quartz, or an artificial byproduct. From here, apply UV fluorescence under long-wave and, if available, short-wave conditions. Photograph the reaction. While fluorescence alone isn't definitive, a blue response paired with correct conductivity dramatically increases confidence. Conversely, green or no reaction alongside electrical conductivity raises red flags. Run specific gravity if conditions permit. Use a small container of water, a fine thread, and a scale to measure weight in air versus weight in water. The formula, Sg equals weight in air / weight in air, weight in water. A reading close to 3.5 suggests diamond, 4.0 points to corundum, 2.6 likely indicates quartz or glass. Always perform this test on the cleaned, post-burn core to avoid coating interference. Throughout, maintain a test log date, location, method, result. Even if a specimen doesn't prove out, it contributes to a pattern. If multiple tests from the same region yield similar fakes, you've learned what not to chase. If one yields authentic diagnostic traits, the whole area gains renewed focus. This workflow isn't rigid, it's adaptive. But each step should build on the previous, refining the hypothesis and preserving test integrity. Heating becomes the gateway, not the gamble. The specimen looked like a textbook win, pulled from a drainage ditch downslope of an abandoned kimberlite exploration site. It had the right weight, a vitrified exterior with shallow blistering, and a faintly geometric profile under grime. After an initial scrape showed no color zoning, the decision was made to apply heat. The coating responded exactly as expected. Micro-crazing within 30 seconds, followed by partial flake-off under a controlled flame. The exposed surface shimmered with adamantine luster. Everything pointed to diamond, and yet, every follow-up test failed to confirm it. The conductivity probe delivered a puzzling result. Thermal conductivity was within range, but the electrical probe triggered weakly, an ambiguous signal. Under 365 nanometers long-wave UV, the core gave off a muted yellow-green fluorescence, inconsistent with the typical blue of many natural diamonds. Suspecting synthetic moissanite, a second, calibrated tester was deployed. Same result. SG testing showed a value of approximately 4.1. Too high for diamond, too low for zircon. Now the profile no longer fit anything cleanly. At this point, assumptions collapsed. This was no simple fake, no common simulant, and no easy discard. The material was hard enough to resist a carbide scribe, showed directional luster, and had survived direct flame without surface dulling, uncharacteristic of quartz or glass. But it didn't behave like any natural diamond. That's when a third-party analysis was pursued. The specimen was sent to a university geoscience lab with access to Raman spectroscopy and electron microprobe tools. The results brought clarity and surprise. The core was yttrium-stabilized zirconia, YSZ, a dense, synthetic ceramic used in industrial applications, especially as a refractory or thermal barrier material in high-temperature environments. Its high density, SG 6.0, had been masked by internal porosity, skewing the field SG reading. Its high luster and flame resistance had mimicked diamond almost perfectly. The original coating? A thin rind of thermally altered slag glass, likely from an industrial incinerator load dumped decades earlier. This single failure carried deep implications. The field team had followed correct procedure, but the source context was the flaw. What had appeared to be a kimberlite downslope was actually contaminated fill from a former smelting test site, backfilled with incinerator residue during 1980s infrastructure work. Without thorough historical land use data, the geology had misled the search entirely. From that point forward, an additional step was introduced to the workflow: land provenance screening. Satellite imagery, soil survey overlays, and historical industrial maps were added to the toolkit. Before any specimen entered the thermal phase, the context of its origin was re-evaluated not just geologically, but anthropogenically. Many industrial materials today exhibit properties previously unique to gems: hardness, luster, thermal resistance, thanks to advanced ceramics, synthetic refractories, and engineered composites. This case didn't discredit thermal melt testing, it refined its guardrails. It also raised awareness of a new class of false positives, especially in urban or post-industrial zones. Coated materials may not always conceal natural minerals. They might hide engineered cores with equally deceptive characteristics. The survey grid had been set with precision. A 1.2-kilometer stretch along a mapped kimberlite dike, identified through historical drilling logs and supported by stream sediment anomalies showing elevated chrome and garnet counts. The team's assumption was sound. The dike's flanks, exposed during recent road cutting, should yield at least indicator minerals, if not weathered diamond-bearing material. For 2 full days, sieving, magnet sweeping, and hand sampling turned up little more than serpentinized matrix and fractured peridotite. The indicators were there, but no payload followed. That's when the reversal began. What triggered the shift was an offhand observation at the lunch site. Several dull, pitted stones clustered near a pile of excavation debris beside a decommissioned bulldozer track. One specimen, roughly 3.5 centimeters across, exhibited unnatural symmetry and unusual heft. Initially dismissed as slag, it had settled in with other waste rock pushed downhill during trenching. The coating was reddish-brown, with embedded fragments of crushed olivine and pyroxene, common in mining debris. But unlike most industrial fragments, this stone showed directional sheen and resisted abrasion. Thermal exposure was attempted on-site using a portable butane torch. Within 90 seconds, the coating blistered unevenly and fractured along an internal octahedral plane. Beneath, a partially exposed core reflected a cold metallic luster, too sharp for glass, too precise for quartz. The result forced a re-evaluation of all previous assumptions. The dike itself, though mineralogically interesting, may have been mined out decades prior. But the debris from that operation, shunted, buried, and forgotten, was never tested. The new plan reoriented the entire grid. Instead of focusing on the mapped dike, the team mapped and sieved the lateral spoil slopes. Multiple fragments of coated material were recovered within 60 meters of the original launch site. Of these, 2 showed melt blister behavior under flame and revealed hard, dense cores. 1 specimen cooled within seconds to ambient touch. Classic thermal conductivity behavior consistent with diamond. A field tester confirmed no electrical conductivity and strong thermal transmission. UV response, blue under LW. Specific gravity, 3.49. It was rough diamond, encased in an iron silicate shell, likely overlooked during previous mechanical processing. This find altered not just the day's tactics, but the region's valuation. Previously considered exhausted, the debris zones had never been fully screened for tailings bypass or equipment loss. Historical records showed that the original operators lacked optical sorters or advanced particle differentiation, meaning smaller diamonds or those obscured by refractory coatings could easily have passed through undetected. The reversal also reframed risk logic. Instead of sinking resources into deeper trenching of low-yield terrain, the focus shifted to low-effort reprocessing of discarded material. Thermal peel tests on surface samples, once considered a marginal method, proved decisive. They allowed rapid triage: burn, observe, test, discard, or escalate. Within 5 days, 5 more confirmed specimens were recovered, ranging from 0.7 to 3.1 carats rough, all with heat-reactive coatings that had masked them from traditional screening. The lesson: not all barren ground is empty, and not all debris is worthless. Thermal behavior, when interpreted in context, reveals more than just mineral identity. It can uncover operational blind spots, misclassifications, and marketable assets buried in plain sight. The principles that guide individual field tests, thermal reactivity, conductivity checks, density measurement, are not isolated tricks. In fact, they now underpin some of the most cost-effective large-scale diamond recovery programs across both private sector mining and state-run reclamation efforts. What began as experimental fieldwork with torches and test kits has been formalized into modular workflows optimized for overlooked or marginal grade material. These institutional adaptations prove the same logic scales, if the signals are interpreted correctly. Take, for instance, the reprocessing protocols used in Southern Africa's legacy fields. Several mid-size operations now dedicate entire recovery loops to buncoat materials, stones with heat-reactive outer shells that defy optical sorting or X-ray fluorescence systems. Their process begins not with high-capital crushing or laser scanning, but with thermal stripping units, rotary kilns or induction panels that gently heat matrix-bound material to 400 to 600 degrees Celsius in a low-oxygen environment. This step causes vitreous coatings to fracture and slough off, revealing any underlying high-density cores, which are then passed through conductivity gates and density sorters. These workflows were informed by field observations nearly identical to those described in topics 4 through 7. That certain diamonds consistently evade detection when coated in silicate or iron-rich shells. Institutional geologists confirmed through SEM imaging and thermal microanalysis that these coatings are not only common, but highly variable, even within a single mine. That variability made one-size-fits-all approaches ineffective, hence the adoption of modular thermal testing cells as a triage step. Stones that pass are routed into secondary assay. Those that fail are reclassified for industrial sale or discarded. Government-run reclamation programs have followed suit, particularly in regions where environmental mandates require tailings cleanup. In Canada's Northwest Territories, for example, post-closure site audits revealed significant diamond loss in old tailings ponds due to historical equipment inefficiencies. As a result, pilot recovery programs now integrate thermal peel diagnostics into their core sampling strategy. Crews heat sample sediment concentrates at grid points using controlled burn stations. Material that shows melt line reactivity or density anomaly under post-burn inspection is flagged for full lab processing. The payoff: higher recovery rates from material once written off as processed. Academic studies have validated these methods too. A 2022 paper published through the University of Queensland demonstrated that rough diamonds encased in iron titanium oxides could resist standard XRF and optical sortation, but would consistently reveal themselves through low-temperature blistering and rapid cooling behavior. The field team that informed the study used a variant of the same torch and probe workflow described earlier, confirming that with careful control, handheld diagnostics could produce lab-level confidence in the field. What ties all these efforts together is not technology, but logic. Begin with the behavior of the outer layer and work inward. Field thermal tests allow rapid separation of high-potential samples from background noise. Combined with basic conductivity and density checks, they form a compact, reliable suite that informs whether to escalate a specimen to costly lab analysis or let it go. The field doesn't wait for perfect conditions, and budgets don't wait for perfect stones. That's why the institutions that succeed have learned to trust behavior over appearance, and to chase signals, not assumptions. It started like so many others. A thermal peel revealed a glint beneath a blackened crust. The blistering was textbook, surface crazing, then fragmentation along predictable fracture paths. The exposed core cooled rapidly, resisted abrasion, and showed sharp, clean surfaces under magnification. Under long-wave UV, it fluoresced a weak but acceptable blue. The thermal and electrical probes gave no contradiction. By all metrics, the specimen appeared to be a small, industrial-grade rough diamond. But this one had a paper trail. The stone was presented to a boutique gem dealer in Antwerp with a batch of similarly coated materials, allegedly recovered from artisanal workings in the Central African Republic. The seller claimed the stones had been overlooked during initial screenings due to coatings formed in iron-rich soil and fire-cleared terrain. The story aligned with known geochemical patterns, and the specimens exhibited melt behavior consistent with natural coatings. But a sharp-eyed appraiser flagged one critical inconsistency: fluorescence under short-wave UV. It was too stable, too uniform, across the entire surface. Natural diamonds rarely glow in perfectly symmetrical saturation under both UV regimes. This was the first red flag. Upon further inspection, the exposed diamond displayed facet doubling under a high-magnification gem scope, a subtle optical distortion indicative of double refraction, not found in diamond. A Raman spectroscopic scan confirmed the truth. The core was cubic zirconia, coated in a thin layer of thermally reactive resin and silicate designed to mimic natural rind behavior. The coating had been doped with trace elements to fluoresce appropriately, and the entire assembly had been stress-treated in a kiln to produce microfractures that looked natural when heated. What made this case particularly dangerous was its precision. The coating had been engineered to mimic the failure modes of volcanic glass and iron oxides, blistering, flaking, and fragmenting in visually authentic ways. Even the density check had been manipulated. Tiny air voids in the core structure brought the specific gravity down to just above 3.5, close enough to diamond to pass a rough field calculation. This wasn't just a clever fake. It was a deliberate exploitation of the thermal melt test itself. The perpetrators knew that many buyers and field agents rely on rapid verification protocols, and that once the outer shell was gone, most would move forward on visual assessment and a couple of tool readings. They also knew that rough, coated stones with a plausible origin story were less likely to be sent for full assay, especially if offered at a deep enough discount to entice quick action. The fallout was limited by timing. Because the specimen was flagged during initial evaluation, the batch was intercepted before wider distribution. However, It prompted a round of protocol revisions across multiple buyers and labs. Thermal testing remained valid, but from then on, it had to be paired with optical isotropy checks and confirmed Raman or FTIR scans for higher-value specimens. Importers also began to require more rigorous documentation of origin, including GPS-tagged recovery logs or chain-of-custody photos from field to bag. This case wasn't the first counterfeit to fool field tools, and it won't be the last. But it underscored the importance of redundancy in the process. Each test tells part of the story. Together, they build a defensible conclusion. Not all coated diamonds are accidents. Some are the geological result of precise pressure-temperature histories that favored both the preservation of the core and the accretion of a thermally vulnerable outer shell. Understanding where these conditions occur and why can elevate prospecting efforts from random luck to targeted success. The key is recognizing the interplay between diamond stability and host rock behavior during transport. Certain terrains foster this combination better than others, producing rough diamonds that arrive at the surface protected but hidden. The starting point is deep, the upper mantle, where diamonds form under high pressure and low oxygen availability. But what happens after formation matters just as much. In volcanic diamond pipes, primarily kimberlite and lamproite, the transport mechanism to the surface occurs via rapid, volatile-rich eruptions. These eruptions are violent, mixing superheated gases, silicate melt, and fragments of deep rock. Diamonds caught in this process are often embedded in a slurry of pyroclastic material, carbonates, and oxides. In certain cases, particularly with low silica kimberlites, diamonds reach the surface coated in magnesium-rich minerals like serpentine, talc, or even chlorite that later alter into brittle crusts. These coatings often develop microfractures during cooling, which predispose them to thermal breakdown. In other pipes, especially those intersecting shallow aquifers, hydrothermal overprinting adds silica or iron-rich rinds. These form through superheated groundwater reactions, creating vesicular or glassy skins that visually resemble volcanic tuff or slag. It's these altered zones, metasomatized kimberlites or pipe margins, that most frequently yield thermally reactive coatings. In lamproite systems, where potassium and volatiles are even more dominant, the coating game changes. Here, diamonds may emerge with crusts rich in sonidine, lucite, or feldspathoid phases, minerals that degrade quickly upon heating or weathering. These environments are particularly prone to producing coated diamonds that mimic river cobbles or frosted quartz until subjected to thermal stress. Lamproitic terrains in Western Australia, India, and parts of Tanzania have all produced such specimens. Outside of volcanic pipes, another major source is metamorphic collision zones, regions of deep crustal compression where graphite-rich rocks are transformed into microdiamond-bearing schists or eclogites. In these contexts, diamonds rarely form coatings during their creation, but may develop them during exhumation. As these rocks ascend slowly through ductile crust, retrograde reactions can deposit mica, iron oxides, or amorphous silicates onto the harder diamond surfaces. These are often highly responsive to heat, breaking down in predictable ways that reveal embedded crystals. If you know what to look for, alluvial and fluvial systems play a final role. Coated diamonds found in riverbeds or beach gravels often owe their outer layers to post-eruption accretion, iron-rich muds, clay fines, and bioorganic films that over time cement into ferruginous nodules or claystone rinds. While less dramatic than volcanic coatings, these sedimentary shells are still highly thermal reactive. Their location in paleochannels or heavy mineral traps makes them valuable secondary targets, especially when upstream volcanic sources have been depleted or obscured. Knowing the geology helps filter where to search and how to interpret what's found. A diamond coated in sonidine suggests lamproite. One rimmed in serpentine might trace back to an altered kimberlite pipe. A ferric clay, rind implies sedimentary reworking and downstream transport. Each tells a different story, and each demands a different testing strategy. Most diamonds don't sit waiting in plain sight. They travel. And during that journey, their coatings, contexts, and concentration zones change. To find coated diamonds that benefit from thermal testing, you have to read the terrain like a transport map. The key lies not just in where the pipes are, but in how erosion, water flow, and sediment sorting deposit the material in overlooked accumulations. In the same way gold prospectors follow placer logic, diamond seekers must understand how coated stones settle in traps far from their volcanic origins. Start with meanders, bends in rivers where flow velocity changes abruptly. On the inside of these bends, water slows and drops heavier material. Magnetite, garnet, and occasionally coated diamonds. Unlike gold, which hugs the bottom, coated stones are more erratic due to their variable density. But in areas with coarse gravel, especially near bedrock exposures, heavier than expected stones often concentrate at or near the base of bars. Test here using number 20 or number 40 mesh sieves to isolate larger fragments. Then examine for unnatural geometry, iron-rich surfaces, or density anomalies. Beyond modern rivers, the most underutilized zones are paleochannels, ancient riverbeds buried under sediment or exposed in cut banks and terraces. These often contain older, reworked diamonds with thicker, more weathered coatings that respond strongly to heat. If quartz cobbles show intense staining or iron oxide cementation, dig deeper. Coated diamonds can be trapped in these compacted gravels, where surface indicators like chromite or ilmenite may still linger in the fines. Alluvial fans, where narrow gullies empty onto broader plains, also serve as catchment zones. In kimberlite fields, fans adjacent to eroded pipes can contain fragments pushed downhill by water or mechanical removal. Coated diamonds often blend with slag, peridotite chips, or basaltic fragments here. Use magnet sweeps first to remove high iron waste, then sort by hand for oddly shaped or overly heavy stones. A good fan will offer a mix of contexts: uncoated heavies, oxidized matrix stones, and the occasional composite specimen that hints at a core worth burning. Scree slopes below exposed kimberlite pipes or trenching sites deserve special attention. These debris cones, often ignored due to their loose, unstable footing, accumulate material dislodged by weather or outdated blasting. Many coated diamonds get mechanically tossed from processing sites or simply bypassed during early screening. In these areas, gravity is your ally. Target zones where material seems unnaturally sorted or where prior grading activities may have stalled. Don't overlook anthropogenic terrain. Old loading ramps, washed-out gravel roads, and culvert outflows near former mining operations can contain forgotten rough. During transport and processing, coated stones were frequently misidentified and used as fill or road base. Where erosion has exposed these layers, you'll often find vitrified coatings now flaking or oxidizing. A perfect case for low-temp burn-off trials. In all these zones, terrain tells a story. Where water slows, where gravity collects, where industry forgot. These are the places coated diamonds go to hide. The thermal test doesn't find them alone. It works best when guided by logic, context, and the patterns of natural sorting.